All right, guys, more on probability and the normal model. Before you start watching the video, go ahead and get StatCrunch up. We're going to need it. That's the way we're going to work these probability problems. So you can, typically in a class I would stop and let everybody get that, but in this format we don't need to do that because you can just pause me, okay? So anyway, back to gestation periods. We saw in the previous video that these things are approximately normally distributed, with a mean of 266 days and a standard deviation of 16 days. And I've already gone ahead and drawn the distribution because I know you're probably getting sick and tired of me drawing this for you. We saw earlier that roughly the probability that a gestation period is between 266 up to 282 was about 0.34. Now, what you can see, first of all, very important, few important principles for normal distribution. So let's just call it important characteristics. On a normal model. Number one, these things are always centered at mu. So again, the mu here is 26, so the distribution is centered at 266. Okay. They have asymptotic behavior. Something I mentioned in a previous video, meaning that if you draw these things correctly, this line right here gets closer and closer and closer and closer to the x-axis, but it never touches it on either side. Now, if you get sloppy and go ahead and draw that like that, make it touch, I'm not going to flunk you or anything, but it shouldn't be like that. This should be asymptotic. It gets closer and closer and closer, but never touches. But the really important is the area under the curve is equal to 1 unit squared. So if we think about this area right here, again, from here to here is 68%, telling me that this is 34% and this is 34%. Well, 34% is equal to 0.34. So if I want to think about this in terms of percentages, I can think of this probability as 34% out of 100%. If I want to think about it in area, I have 0.34 of the area over 1, so the probability is 0.34. Either way, you end up at the same answer of 0.34, okay? But important thing that we need to know, the area under the curve, even though these the curve doesn't touch the x-axis, the area under the curve is 1 square unit. Now, let's go split screen here, and I want to bring up StatCrunch, and I've already got it ready here because I knew where we were headed, and I'd like to work this a little better, okay? Because using the empirical rule, I tell you that roughly the probability from 266 to 282 is 0.34. But let's get it a little better. What if we can come in with, well, I'd like to know more precisely. Well, more precisely, we don't use the 68, 95, 99.7% rule. That gives us an indication. It gives us a rough estimate. Pretty good estimate, but it's a rough estimate. I want to tighten this thing up and get more of an exact answer using technology. Well, how would I do that? Well, guys, it turns out if we go to a blank table, we have some really, really, really cool stuff here. If we go under stat, and go to calculators, we can come down to a normal distribution. Look at all the distributions that StatCrunch includes: beta, binomial, Cauchy, chi-square, discrete, exponential, gamma, geometric. I mean, all kinds of distributions, but we're focusing on the normal distribution. So if I click that, what's going to happen is it's going to come up a calculator for calculating probabilities. Now, if I do the standard measurement, or I can do the between measurement, the between measurement allows me to calculate the probability between two values. The standard measurement gives me the option of calculating above or below one particular value. Well, guys, clearly in this situation over here, we need between. So I'm going to put in the information. The mean is 266. The standard deviation is 16. I want between 266 and 282. Compute. You'll see that the area it gives us starts at approximately 266, just like the drawing over here. But it shades it in red instead of shading it the way I shaded it. And notice that approximately we were 0.34. The more precise answer is 0.34134475, and so on and so forth. So we get a much tighter answer over here. We get a much better answer. Now let's just work some problems, and let me show you how it all kind of unfolds. Okay. It's a thick sheet of paper. I thought there were two sheets of paper there. All right, so let's just get a completely different problem here. ACTs form a normal distribution, mean 20.6, standard deviation 5.9. What's the probability that we get an ACT greater than or equal to 20? Well, guys, that's going to be hard to do without technology. But with technology, we'll go over and we'll choose the standard. We'll put in the mean of 20.6. We'll put in the standard deviation of 5.9. Now, less than or greater than, we need greater than, so we need to choose that. We want greater than 20. And we will hit compute. So the correct answer here would be 0.5405. So what this tells us is we close our eyes and we choose one student at random. The probability that that student has an ACT greater than or equal to 20 is 0.5405. So about 54.05% of students has an ACT greater than or equal to 20. So guys, we can interchange the whole probability and percentage, because probabilities, which are given in decimal form or fraction, can easily be converted to a percentage. So we can describe the percentage of students in our entire population who have, in this case, an ACT higher than 20, or we can refer to the probability of randomly selecting one student, and that student, him or her, having ACT higher than 20. What's the probability that we select a student at random and their ACT is less than or equal to 28? Well, again, that's a tough problem without technology. but we can come in and check this to less than or equal to. Change that to 28, hit compute, and 0.8951 is the probability. Now, what if we had probability of ACT greater than or equal to 28? What would we do? Well, we could use technology, or we could just see that because this is the complement, over here on this graph, see where I'm going here, 28 would just be that area that isn't in red, and since we know that the entire area under the curve is 1, we can just take the 0.895, subtract 1, and let's see what we get, 0.1049, if my mental arithmetic is correct. Or you might say, I don't like that. Okay, well, if you don't like that, just change this, compute, and you get your 0.049, again rounded to 4 places, 0.1049, I'm sorry. What's the probability we get an ACT between 20 and 30? Well, it's pretty easy, right? Choose between. Put in 20. Put in 30. Hit compute. So the probability is 0.4849. Now, guys, let me tell you the difference between empirical probability and theoretical probability. Let's say that and this is kind of like the difference between a sample and a population. Empirical probability, our event is flip a coin. We flip a coin 6 times and we get a head, a head, a tail, a tail, a tail, and a tail. What was the probability that we got a head? Well, we got a head 2 out of 6 times, so the probability is 1/3, 4.333, or 33.3% of the time we got a head, right? Empirically, though, we talk about a probability based on a particular sample space. Theoretically, we know that the probability of getting a head is 1/2. The difference is the empirical probability takes something that has occurred and looks at the likelihood, the probability of getting a particular occurrence from that, an event from it, where a theoretical probability looks at if we could repeat this over and over and over and over and over and over, repeat this experiment forever, what would be the theoretical probability we would get ahead, which is 1/2. So empirical means we did it. We're looking at the probability only on the sample space of what we created. A theoretical probability gets into the theoretical distribution and talks about the probability or likelihood theoretically. Guys, the reason I tell you that is these answers we get over here are theoretical probability answers. They're theoretical answers. So it's a theoretical probability. Okay? I hope that didn't go over your heads, but I don't think it did. So guys, just kind of a learning, make sure that we're all on board right here. Let's take a look at IQs. So what's the probability someone is selected at random and they have an IQ above 130, greater than or equal to 130. So essentially, if you remember, 130 gives you the title of being a genius. So I've always thought, well, what about the poor guy or girl who has an IQ of 129? They're probably just as smart as the person who has a 130, but again, we cut this stuff into two chunks, genius and not genius. So the one person with the 129 isn't a genius, but you get that extra point, you are a genius. So that always seems a little wacky to me, but that's just the way life works, right? So what's the probability that someone is selected at random and they are eligible to join Mensa, right? IQ of 130, they're genius. So guys, should be pretty easy right now, right? Do we need between or standard? Well, we need standard because we're looking at just one measurement. So the mean is 100. The standard deviation is 15. We want greater than, so keep that. And we want 130. Compute. So the probability is 0.0228. You can also think of that as what? Think of this as a percentage. 2.28% of people has IQ greater than or equal to 130. So again, probabilities and percentages are kind of interchangeable. The probability talks about the randomness of selecting one person and having an IQ, in this case, greater than or equal to 30. The percentage talks about the entire distribution, all the population. Of all the population, what percentage of them, in this case, has an IQ greater than 130. So again, up here we're talking about one person. Down here we're describing the entire population, the entire distribution. Guys, that's all I have. Hope this wasn't too painful. I don't think it was. Take care.